Portable XRF and data quality, QA/QC. I talked about this with Michael Gazley, who runs a Portable XRF course that I suggest you check out. I got talking to him for about half an hour about how this all works and how we integrate quality assurance and quality control in the collection of Portable XRF data. Anyway, I forgot to include or record an introduction, and here I am on site in West Africa in 45-degree heat, doing my best to set up the scene for this conversation. I hope you enjoy. Let's get into it.
We've got this Portable XRF instrument sitting here on the table in front of us. So, in the context of that, maybe we'll frame this conversation rather than just talk about QA/QC in its most broad context. But we should probably start there as well. But, do bring it back to this.
I think it's a good point because everything is about purpose, and particularly with this instrument, it's all about what you want to get out of it. And based on that, you need to set your targets. So it's a good discussion. Can get as complicated as you want. We can get lost in the weeds, but you're quite right. We should focus on what we want to get out of this and what users need to get out of this. So, yeah.
And that really comes down to a data quality objective, right?
Yeah,
we need to, before we start collecting any data or any workflow really, whether it be involving a Portable XRF or not, we really should be framing what the quality of the data is that we want to get back from that process, don't we?
It's a key problem, not just for pXRF, but anywhere in the industry, because we collect data and we have certain expectations of the data, right? And we're going to use the data for a purpose. And if we talk about quality assurance and quality control, we cannot frame that conversation without knowing what the purpose is, because if you don't know what quality data you're targeting, then you don't know how to control it either. It sounds so simple when you say it in those few sentences, but it's lost in translation a lot of times because we work in very dynamic environments and we just collect data because that's how we've always done it, and we end up with data in a spreadsheet and that ends up in a model and people do stuff with it, and it's difficult to translate that to a step-by-step process that is actually pragmatic in the field and actually links back to that purpose so that you can actually make some sound decisions based on the data.
And I guess if you're going to start implementing Portable XRF on a work program or on a specific project, you have an opportunity to stop and think about what the data quality objective might be, what the purpose of those data are. Why are you collecting them? Is it anomalies, or is it lithologies, or is it alteration? What are you trying to extract from those data? And all of those different things are going to have different quality requirements, aren't they?
Well, it's very important. I mean, you can come up with a few examples because that helps a lot in setting the tone for this conversation. But for instance, if I would be on an RC drilling program and I am interested in pre-screening my sample selection to some degree for whatever element of choice you're trying to sample for, then you could use the instrument as a very simple, almost binary pre-selection technique. And at that point in time, I would probably worry less about some of the real strict quality control procedures because I'm not going to put the data in models. I'm not going to inform investors about it, hopefully. So you need to know what the purpose is. And in that case, if you zap to the bag, as I'm sure you will be explaining, that's a bad thing because you have all sorts of effects happening. But it depends, and it depends on the time that you have and what you want to get out of this, right? So if you're running a SOL program and you're actually going to make some pretty critical investment decisions based on where you're going to infill sample, where you're going to drill, I would probably build in some more strenuous control processes and I would change my approach a little bit. So you're right, everything comes down to purpose. And there are even some elements, obviously, where it's actually not that far away from where we are now to be using the data coming out of the instrument to inform investors and models. We're not very far away from that with the techniques that are currently available to us. So all those three end members have different purposes, and you need to set that in what we call data quality objectives. And that needs to be part of the entire data quality management system that one has when you do any exploration. What is the system that controls the data? And it starts with the DQO, the data quality objective. Yeah.
So let's continue on through the data quality management system. We're going to start finishing up talking about QA. and QC, and I should probably provoke you with your favourite phrase, a QA/QC sample doesn't exist.
That's right.
Perhaps you should explain why it doesn't exist, and what the differentiation between QA and QC is, and then we can discuss those individually.
Yeah, sure. And look, it can get quite complex, so it's hard to break this down in simple terms in only 30 seconds. But the key to me is this, right? I always described the key difference as being a timing issue. The QA is something that you do before you start measuring or collecting data, right? This is all about collecting data and the process. So you have a process, and that process has a timeline. You start collecting data, and T is on the x-axis, if you like, with an arrow to the right. And that is the process as it happens. So that is a time slot on a continuum, if you like. The QA sits before that. I like to picture it like that. So that's the SOP, the standard operating procedure, that tells you what you need to do to make sure that you don't introduce variance or errors, if you like, and bias. That's what the purpose is of QA. Incidentally, there's a really nice video that makes this point very clear. It's a father with his 2 kids, and he asked them to write an SOP on to make a peanut butter and jelly sandwich. And I can see that you've seen it, but it's hilarious because obviously the kids write something down and he tries to follow it, and it turns into a disaster every time because the kids are not specific at how the steps need to be followed. And what then happens is that you make mistakes. And in our world, mistakes are either increasing the variance in our data, which is bad. Variance is not good, right? Variance is the resource killer. And we don't want bias, because if you do it incorrectly, that means there's a bias, and that leads to incorrect decisions. So the whole purpose of QA is to set that scene and set those rules up before you begin, so that everybody that is involved with collecting the data and every instrument that is involved is properly calibrated and people are doing the right things. And that limits your variance in your data, which is a quality designator. Variance and accuracy are quality designators. And if your variance is low, you have good quality data. If your variance is big, you have bad quality data, right? From a binary perspective. So that is the SOP QA part of it that starts before you do that before the process starts. Then you get into the process, and that's QC. And as you see many people commenting, it is not 6 months later when somebody...
It's not a post-mortem.
It's not a post-mortem. It's not somebody sending you a database. And we get these emails dozens of times a year. Can you do some QC on this data set? No, I can't, because you collected these data many, many months ago. I can only tell you how it died. I can't do anything else to that. So the point is, QC happens when the process is in operation. And ironically, for as much flack we give the laboratories, that's what they actually do. Because in the most classic, simple example format, an AAS machine is sitting there, there's a calibration process happening, and samples go through, and flags either raise when some rule is broken, and then somebody would see that and they would stop it and they would fix it. That's the purpose of QC, stopping something when it is out of control, and then fixing it so that the process can continue. So the whole principle of in control and out of control is fundamental to QC. And you can only do that whilst the process is going, and not when it's completed.
So let's unpack that a little bit around one of these devices. QA, as you've just outlined, is obviously having good SOPs and a good workflow that fits your DQO, your data quality objective, to make sure that your data are going to be good enough to do what you want to do with them once you've collected them.
Yes.
That's all set up before you even get this thing out of the box. Then we're going to think about the QC. We're going to be analysing samples, we're going to be analysing reference materials so that they could be certified, they could be not, they could be internal. Let's just call them reference materials for the purpose of the conversation. That we're going to use to do two things. First, we're going to calibrate the data, as the lab would do with its AAS machine, as you just mentioned. They're going to analyse standards, calculate a calibration factor and apply it. We've got to do that step. Then we also need some reference materials to make sure that the instrument is performing properly. I guess the challenge here is that I expect that instrument to drift through time. It's an analytical piece of equipment. It is going to perform slightly differently day to day. over the course of a year, the X-ray tube's probably is going to get older and its performance may drop off a little bit. You'll see some drift. That's expected, right? But so we need to be thinking about, as you framed very elegantly earlier, what kind of gate do we need, or how are we going to collect or do QC as we're collecting the data to make sure that we don't collect a whole bunch of poor quality data with high variance that we can't do anything with?
Yeah. Yeah, look, it's a fundamental question, and it's very important here to pin everything on the principle of purpose, right? Because like you said, you have different expectations. You're not bringing a multi-million-dollar laboratory into the field. It's a handheld thing that sits in the holster, right? I mean, that sets the scene a little bit for what you can expect from this. A very powerful instrument for a lot of for the right purposes, but that already sets the scene for how you need to treat your QC. And the whole principle of QC is to separate what we call special cause variation from common cause variation. And that means, very quickly, that if something happens that is not just due to random noise, you want to pick that up and use that to demonstrate that something isn't right and that the instrument is out of control. And we would usually apply a bunch of statistical rules to that would help you with that, because you can talk about it, you can talk nicely to the instrument, but it won't give you that feedback unless you set quantitative thresholds, right? So this is the principle that we're trying to unpack here. How do you set quantitative thresholds that actually are fit for purpose? Because what you don't want to do is set thresholds that then every 3 seconds say that something is wrong with the instrument, because then that's not the purpose. Some things are allowed to be more wrong than in other situations, if you like, if you want to phrase it in a bit of a clunky way. And that's very important, because the one problem in the QC interpretation in our industry is most people are very dead set on this 3 standard deviation principle, and everything surrounds it. But if you're married to that, then you can't really do anything here, because that's not what this is about, right? So with the instrument, you would have to be setting your own rules that are purposely built for the situation that you're in. And like you already say, usually in a laboratory, you would want to find drift, and you would want to nail that pretty quickly. You don't want to wait for a month for an instrument to drift, because there's a lot of samples and a lot of money involved reassaying that. So you want to pick that up after 6 or 7 or 8 or 9 samples over the course of an hour or 2 or something like that. It's not really how it works, but for the purpose of this discussion. With this instrument, things can drift a little bit, because there are techniques that we must use anyway to correct the data, as you're going to get into soon anyway. So we're going to look with these rules that we're setting to find different things, and they're probably a bit wider than you would otherwise expect from your classic fire assay process at a lab or something like that.
Yeah, so I mean, for me, there's 2 key parameters to control when you're collecting your data, to make sure that you haven't gone and collected a whole bunch of low quality data. You want to make sure that the instrument's clean. We need to be analysing a blank. Yep. And that's just, from my perspective, comparing it to yesterday's performance. Have more elements appeared on my blank, i.e. on the detector or on the window of the instrument, than they were there yesterday? Yes or no? Very binary question. Simple QC check, I think.
Yeah.
Then the next question is, as you suggested, we need some kind of performance gates on a reference material. And I recommend to people that they have a reference material that is always analysed, irrespective of what kind of samples are being analysed, be they felsic or ultramafic. Just nominate a reference material that's always done, and you can look at the performance of that compared to yesterday and the day before and the day before that. And as you say, perhaps set some sensible performance gates. Perhaps you could comment on.
Yeah, so this is the trick, right? Because now we're using words and sensible performance gates, right? Now we have to somehow translate that into a system that you can write in an SOP, so that the technician in the field can apply that and make sure that it gets applied properly. Because if you turn it into a PhD on statistics and so on, you make it so complicated that you defeat the entire purpose.
Well, and then we're not actually getting control, because the person in the field is going to So stuff this document.
Yeah.
It's too difficult, too complicated.
Exactly.
Move on.
So what we need is to translate some simple rules. And for instance, if you look at Marat Epsilov's classic paper with some key images on CRM data, I'm sure a lot of people have seen it, but there's a really interesting, really educational one in there where the data plot, at the same sort of level, if from a grade perspective, and then suddenly there's a big jump and it sits, at least a factor 2 higher. Well, that's the sort of thing that we're talking about here. That is a quantitative jump that is so disproportional that something clearly isn't right, and then you have to stop and figure out what's going on. But I just want to put that against the classic situation in a standard laboratory where we're actually looking for far more nuanced, small statistical occurrences that could mean something is not in order. If you apply that level of rigor to a portable XRF instrument, you're going to sit there with the instrument on standby every second of the day, right? So it is, how do we translate those rules? And there are some simple things you can apply to that are easily built in an SOP and an Excel spreadsheet if you want to go that way. Yeah.
Yeah, certainly in some places I've stuck a list of elements on the wall with some ranges of kind of the week's worth of data that we've just been collecting while we've been setting up the course. And it's not about stop collecting data if it wanders outside this range. It's hey, perhaps we should raise a red flag here and see if tomorrow or the next time I analyze that reference material, is it still that number or has it dropped back down again? Was it part of the natural variance of the system?
Yeah, look, we've got to be a bit careful here. Now, another good example here is an RC drill rig, right? Picture an RC drill rig, which is a very dynamic situation. There's a driller who arguably doesn't want to be tapped on the shoulder every 3 seconds by a zealous geologist that talks about QC of the data. They're there to drill a hole, not to stop every meter and weigh it to 500 grams accurate and then say something about it. However, there are things on an RC rig that you need to monitor, right? I mean, if at some point you're just consistently getting just something really simple, wet samples, right, then something is not working right because, in general, right, if you've got no particular aquifers that you're drilling into or other issues, then something is going wrong and you need to fix it. But if one sample comes out a bit moist, you're not immediately stopping the drilling, right? It's a different purpose and there's a different expectation of the data. You can use samples, the weight of samples on a drill rig, to kind of very loosely see whether that drill rig is producing consistent samples, right? Because the weight of a sample is a proxy for recovery. And if you're not recovering something, you have a problem, and it could mean a mechanical problem, which could mean you stop it. That's quality control. It's the same kind of thing here. It's such a loose environment, you're not going to stop it when one sample drifts off a little bit, because there is a far broader purpose to this and a far broader process. However, if the same would happen at a lab on an AES machine, you would stop it. Right, and if something outrageous is suddenly on the you would have a close look at whether maybe you've mixed the wrong calibration standard into your AES machine. You don't know, but you would stop and fix that. Then, different situations require different DQOs and different quality control thresholds, if you like. Yeah.
So as we move further down the process, we've now collected our data. We've done some QC. We've checked the blanks. We've checked the reference materials performing consistently, making sure there's no significant steps in performance. We mentioned QAT at the start. This is probably a new one for people. Yeah. Do you want to unpack that a little bit?
Yeah, look, I mean, it's we started using this nomenclature internally because after working with some laboratories, there is a quality acceptance process to this to the process of collecting data. Right, and if you get to the point where you acknowledge, okay, we need a purpose, and then we set some SOPs up, and then we control the data. So we get to a point where the collection of data finishes, right? And at that point in time, what we can say is that the data that we have in front of us are all, call it from one population. In other words, we don't have apples and oranges, right? Because it's statistics or modeling something if data from two different populations doesn't work. And by two different populations, I'm not talking about domains or anything, what people might be thinking if they're listening to this, but we're really talking about when something like sample swaps or errors. I mean, I get the question, should we remove that from the data? So yes, of course, because they shouldn't belong there. You should never do statistics on data that doesn't belong there. So the point of QC is that you end up with a data set that is from a process that was in control. Now that means you can do statistics on it. Now you can look at your mean of the data set or the variance of the data set and compare it with something else because it's from the same population, if you like. And that's where I invoke this principle of quality acceptance testing. Now we test whether what you've actually got matches the objective that you set at the start. Because if you said, we want the variance to be of this level, and here I'm talking about, using my hands, talking about a certain noise in the data, which is variance, and it's a certain threshold that you want to expect. You can quantify that. And then you can compare it to how much variance you wanted to accept in the data set, right? But you can only do that if that process was in control. If we have two different processes, you can't compare that. So that's why I separate out quality acceptance testing, and we can use Fisher tests and those sort of things then to run those statistics, and we call that quality acceptance testing.
And that's the place that you would get your data that you've collected on the instrument and then calibrated those data, which obviously is something I'll talk about in a lot more detail.
Okay.
Then you could compare those calibrated data for some reference materials to the expected values of those and make an acceptance testing statement of, are these data close enough to the expected values for the purpose that I want?
Yeah, correct. So, I mean, just to be clear, I mean, there's probably two different stages of that process. First, you want to indeed make a statement of the acceptance of the mean of the data and the variance of the data, right? So that you actually talk about accuracy and precision from an acceptance perspective. Now, then if you get to that point, you accept the data, then you can still decide whether to correct for any bias in there or any trends in there, right? That is a decision that you make that follows that. And in the classic exploration resource development industry, that would be examples of, you've demonstrated bias between diamond drilling and RC drilling on a scatter plot, and you correct stuff if you want to do that. Now, we generally, industry, I say that we're very cautious with that because it's always a relative bias, right? Or biases are never consistent, and there are obviously trends in the data, and you don't know. You've got to be extremely careful with correcting data, particularly in the resource estimation side of things. However, if you build, and this is obviously what you're going to get into in more detail, if you build in a system that allows you to control that correction, then
calibration is probably a better word.
Calibration, yeah, you're right. If you build in some principles and some systems and some processes in that calibration, yeah, then in most cases I would argue that correcting it for portable XRF is perfectly suiting the purpose that you set out to achieve. So, but you've got to be careful with people wanting to take that principle and then correct anything they see out there. You've got to be extremely careful because I think it was Francis Petard actually who ran through this in a course that I attended many moons ago. You got to be careful with biases. So this doesn't apply to all and any data out there, but certainly with the right processes, it does apply to portable XRF.
So if you're thinking about getting some laboratory data on a subset of your samples, as part of the QA, QC, QT process that we've just talked through, you'd be considering that as part of your QAT. You'd be considering how close the calibrated portable XRF data set match the laboratory data.
Yeah, exactly. I mean, and this is not unlike an umpire laboratory test. I mean, if you, for some reason or another, would decide that one data set is better than the other. I mean, if you go to another lab and it's just another lab and it doesn't have anything different, then correcting one to another, you would need to be pretty bold to argue through that, right? But if you're dealing with portable XRF data, and you send a suitably representative subset of those data to a laboratory, and you include enough certified reference materials to assist with your calibrations, because laboratories will have their own control issues that you must be on top of, as well as their own biases, right? So you're started to mix a few things, but in general, yeah, then you can play that game and do that very. You can do that quite well, and certainly would be But you would only do that how important your pXRF data are. So for copper, if you are willing to take that leap, and you can demonstrate that quite easily on a scatter plot, if you like, that will appeal to most people visually. You can demonstrate quite strong correlations. Well, in that case, if the trend is clearly consistent, I wouldn't be against a correction if that process is handled well.
However, if you've calibrated your data properly, the comparison should likely come out very favorably when you compare your Portable XRF data to the lab.
Well, so you can build in various levels of control and further manipulation or calibration of the data, depending on how serious you are to getting that right. If I would run a fairly basic early stage exploration program for gold, and I'm using arsenic as a proxy, I don't care whether the arsenic is 350 ppm or 850 ppm. Is there's a red blob here and a blue blob here? I don't want to be there. I want to be there. I don't need any reference stuff. I'm probably even going to just kick my heel in the ground, point it at the soil, and go with it. Right?
Well, I mean, as I will argue, there is a heap of value to be extracted from doing exactly that, so long as you can just make sure that the performance of the instrument is consistent day to day, so that you're comparing apples with what you collected yesterday with what you collected today. Yes, I think you're completely correct. You can pull back all of your QA and QC significantly at that point, because your data quality objective is
it's different.
It's quite different.
Yeah, absolutely. But you just got to be careful, because if you want to use the data later on downstream and you realize that you actually wanted a bit more resolution, and then you want to see too much in your data, because if you do point something here in New Zealand, that soil with the moisture in it and with some large fragments with a fairly thick horizon that your heel is not going to deal with, you're going to get some pretty bad data, right? And you got to understand data quality enough from downstream to upstream to set up your DQO and your SOPs properly.
And that comes back to metadata, right? Actually making sure that those numbers, when they've made it into your database, are recorded with the metadata that lets other people in the future know that René was out there with his heel, smacking it into the dirt, and that's how those those data were collected.
Well, and obviously to add to that, which is a big thing for us in RSC, report it properly, right? I mean, report it transparently and with enough supporting information so that a reader can understand what you've done. Put some pictures in it, right? And put some images in it, and you'll get there pretty quickly.
So on the subject of reporting and transparency, what about, we've kind of touched it, you hadn't quite latched onto it, but what about reporting, Portable XRF data to the stock exchange, say reporting under JORC or something in that space? Yeah,
look, I mean, many people have covered this, but at the end of the day, it's just data you collected. I mean, the JORC code, the JORC police is not out there to tell us what data we can and can't collect, right? So it's all about the transparency of how we report this. So putting on the front page some copper intervals that you've got from pointing the instrument at half rounded core for 30 seconds, and then averaging it out in an Excel spreadsheet, and on page 5 or deep buried in a table 1 say that they were Portable XRF results. That's probably not cool, right? You can't do that. Putting it in a headline and even swindling with the prominence of the font space in which you express, you got to be clearly out there to make it obvious what you're doing. And there is a very clear expectation that then is in the industry that you do not just point something at core and then report that, regardless of the disclaimers you build around that, right? I mean, at that point in time, you might be, if you're a purist, JORC space-wise, you might be perfectly fine, but the ASX, people will probably take offense, and will your peers, right? It's just not a smart thing to do. You need to understand where this instrument sits in the whole in the whole system, if you like, and then use it appropriately, right? It's not very easy, and it's not particularly explained very carefully in the code or in some white papers, but I think you said a few things about this that are quite applicable.
I've said one or two things.
You said one or two things. Yeah. So I think it's important for people to, you can use the instrument, but again, the purpose is everything, and you've got to know the limitations and not be trying to be too clever from a marketing perspective. And we know when we see one when you're probably a little bit too much on the wrong side of that equation. Yeah.
Well, I think that's a really great discussion, René. Thank you for dropping down from your office to have a chat to me in the studio here. And having a chat around QA, QC, hopefully bringing a few more people to QAT, and the importance of framing your data quality objective ahead of collecting any kind of data, really, but specifically in this case, Portable XRF.
Absolutely, and the field will continue to challenge us as new instruments come out, and the pressure is on with laboratories, having long waiting times at the moment. People want to get results out, and they feel they're price sensitive. So I'm sure this will be a hotly debated area for some time, and at some point there will be a resource that will be based on Portable XRF data, perhaps for an element like copper. And that time will come, and I think we all got to be ready for that and understand how the framework works to do that justice.
I'm genuinely surprised we actually haven't seen it yet. When I wrote my paper in monograph 23 in 2014, or wrote it before 2014, I thought that day wouldn't be that massively far away from then, and we're 9 years on.
Yeah,
and it's still not happened.
No,
we've got a resource that's based on Portable XRF data.
Well, look, it happens in other parts of the industry, right? I mean, if you look at uranium, there's a calibration happening. There's a tool that goes down that measures stuff, and there's an adjustment that you make to those data, and that ultimately finds its way to a mineral resource, right? So we're not far away. But the one thing that you get in this industry, you get this overcorrection where people are scared because they've heard about it, and they've heard about what I always jokingly refer as the JORC police, and then there is this absolute wall that gets built for sometimes no reason at all, right? And yes, people need to be careful, but if you do good science and you understand what you're doing with quality control, there's a lot you can do with this instrument. And that's why obviously we own so many of them, because it's such a beautiful exploration tool. It's the first thing I bought when I set up RSC, was a Portable XRF instrument. So no, look, very interesting, and thanks for having me on the chat.
No worries. Thank you, Rene.
Thanks.